Let's talk about normalization and denormalization, which are not just practical topics, but also kind of intellectually interesting in the area of database management. Let's talk about database normalization in general first. So imagine that we have a table with columns such as order ID, customer name, product name, and price as shown here. At first glance, you can spot several redundancies in the table. For instance, Mike Smith appears more than once, Sarah Jones appears more than once, and so does the product laptop. These repetitions can lead to inefficiencies, making updates and data management more prone to errors. So to reduce these redundancies and improve data integrity while maintaining relationships between these data elements, customers, products, and orders, we can break up the data into multiple tables. First, let's create a customers table. This table will store each customer's information, like their customer ID, name, and email, ensuring we only store this data once. Instead of repeating the customer's name and email for every order, we'll just reference their customer ID in the orders table. Next, we create a products table. This table holds the product ID, product name, and price for each product. By doing so, we store the product details once, and we use the product ID to refer to them in the orders. And finally, we restructure the original data into an orders table. This table contains the order ID, customer ID, and order date to track each transaction. The customer ID links back to the orders table, and the product ID links back to the products table. This process that we just underwent is called normalization. It aims to reduce redundancy while preserving the necessary relationships across the data. This tends to improve both efficiency and integrity in the database. This is one philosophy of how to organize data in a database, but as we are going to see, it is not the only philosophy, and it can come with some trade-offs. So normalization is the process of structuring a database to reduce redundancy and improve data integrity. The way this is done is by dividing data into smaller related tables, each piece of data being stored in only one place. That's what it ensures. The goal is clear: to minimize duplication of data while maintaining the integrity of the data. However, while normalization improves data integrity and reduces redundancy, it does come with a trade-off. It can lead to performance overhead during queries. This is because when data is spread across multiple tables, multiple related tables, queries that require combining information from these tables because they're related may require expensive join operations. These joins can significantly slow down performance, especially when you're working with large data sets. So there's another approach called denormalization. Denormalization is the process of partially reversing normalization by combining related tables into one table. The goal here is to reduce the need for complex join operations when running queries. So instead of querying multiple tables and using joins, denormalization allows you to store more data in fewer tables, sometimes a single table. This can improve performance, particularly when you're working with large data sets where joins might be expensive and time-consuming. Essentially, you're simplifying the query process by reducing the number of tables involved in a query. However, it's important to note that denormalization can also lead to data redundancy. So it's a balancing act between query performance and data integrity. Now we're going to talk about denormalization in BigQuery specifically. BigQuery, now that you know the difference between normalization and denormalization and the advantages and disadvantages of each, you should know that BigQuery actually encourages denormalization to improve cost and performance. One of the reasons it can do this effectively is the type of storage it uses. It uses columnar storage, which allows it to scan data more efficiently than other databases when denormalized. This efficiency in storage and data scanning reduces the need for join operations, which are typically expensive in terms of performance. By minimizing joins, BigQuery can handle larger datasets faster and cheaper. Another key feature that makes this even easier is the ability to use nested tables and repeated fields to store complex data structures inside a single table. That's why I've added the icon of a Russian nesting doll here. It just kind of represents how you can nest tables within other tables, keeping related information together in a compact format. So nesting tables is possible in BigQuery, and we will look at that more shortly. But for now, these nested structures are technically known as a record or struct data type. And if you ever need to analyze or flatten the nested data, what you can do is you can use the unnest function in BigQuery. So while BigQuery does support traditional join operations like usual, and you can normalize your data, it is more efficient to denormalize where possible to fully take advantage of the performance and cost benefits. The ability to take this approach is really one of the reasons why BigQuery is such a unique product in the market. So I just want to take a moment to show what a denormalized table actually looks like in BigQuery. This is a public data set provided by GCP in BigQuery, showing weather forecasts for specific geographic points. Each row represents a forecast for a particular point on the map, and notice that within each row there is a nested table under the forecast column. So we see forecast.hours, forecast.time. That is an indication that there is a nested table within the forecast column. The forecast column is basically another table within the larger table. So it stores multiple forecasted hours and their corresponding temperature values as well. And instead of spreading the forecasted data across multiple tables and then joining them, denormalization allows BigQuery to store all of the related information, in this case multiple hourly forecasts, directly within a single row as a nested structure. For example, this first row represents weather data for a location at latitude 39 and longitude negative 121.75. And the forecast column contains multiple records or sub-rows that track hours into the future, from 0 to 23, the timestamp for each forecast hour, temperature values at 2 meters above the ground. So it's essentially its own table inside of this table, and that's why we call it a nested table. Let's look at an example query of how you would access the data in this nested table. You don't need to really memorize this, but this is just an example of what's unique about BigQuery. So it retrieves the forecasted temperature at 10 a.m. for various geographical points. It starts by selecting the geography of each point and the forecasted time, renaming this as forecast time for clarity. And the key part to note here is the use of unnest forecast, which takes the nested forecast data, including the multiple hourly forecasts for each location, and it expands it into individual rows, one for each hour. Right? So we unnest the forecast array, and then we can easily filter for specific hours. So the unnest function allows us to work with the nested table, the nested structure in the BigQuery table, turning it into a flat structure. All right, I know this might be kind of a lot, but we're almost done here, and I just think this is important. Why now is this more efficient than a join? Well, in a normalized setup, you would have to store the location information, like geography, in one table and link it to another table that stores the forecast data with rows for each forecasted hour. Every query would require a join operation between these tables, which can be computationally expensive, especially if the data set is large. So this forecasted data being stored in a denormalized format as a nested table allows for all the relevant data to be put in a single place, no need for joins. BigQuery's columnar storage efficiently scans only the necessary columns for the query. This allows you to then also retrieve the forecast data for a specific location quickly without needing to piece together, data from different tables. So denormalization in BigQuery reduces the complexity and the cost of running queries in most cases, especially when you're dealing with data like this, large multidimensional data. All right. So how do you decide between normalization and denormalization? Well, the choice depends on the needs and priorities of the system that you're designing. You would choose normalization when data integrity and update efficiency are more critical than query speed. This is particularly important for systems where maintaining consistent, accurate data is a top priority, as normalization minimizes redundancy and ensures that data is only updated in one place. And then denormalization is better when query performance is the primary concern, as in many analytics use cases. And if you think about it, BigQuery is an analytics database. And it's also good for read-heavy systems with large data sets where joins might otherwise slow performance. So keep in mind for the exam that although usually denormalization is preferred in BigQuery, there are cases where normalization is actually more appropriate. And those are covered on the left side of the screen. So just keep that in mind. That's it for this section.